So a detour. Let's take a detour. Enter paths, right? So forget about everything that we did about a regularization and all of that. We will do one simple thing. Imagine a circle. Circle. What is the equation of a circle? Equation of a circle is
x square plus y square equal to r square.
That is right. Let me just write it like this in simple.
Is this in 2 space or 3 space?
I'm just looking at two space for the time being.
Okay.
You can do it in 3 space. It doesn't matter, but let's be very, very simple. Gx, equation of the circle is x square plus y square is equal to some constant. Constant. Let me call this constant r. Well, it is r squared, but let me just say r squared, right? Which is basically the radius of the circle, right? So what happens is that different circles will have different radius, isn't it? That's all it is. All you're saying is all points which are at the same distance from the center define a circle. They define this. Now let's do this. Let's look at this equation and take its derivatives. So we will do, now you notice that this is an equation in 2 dimensions. So how would you take derivatives? You can say that, hey, what happens to G if I just keep y constant and just change x? So if y is constant, the derivative of G, which is with respect only to x, holding y constant would be what? 2x. Derivative of G with respect to y would be 2y.
So is it about the direction, like where the direction?
No, hold on, guys. Just pay attention. Don't jump. Is this pretty obvious? Partial derivative means you keep the other variables constant and you take the derivative. This. Now the definition by definition, gradient, right? So take a point. Let's take a point, some particular point. I'll just take a point x, y, right? Or maybe some special point xa, ya. It doesn't matter. Actually, let me not clutter it with notation. So just assume that some point P is this. Are we together? What is a point? A point is a vector P. Would you, that part is also obvious. This is the P vector and this is the point P. So a point and a vector are the same thing, right? This is one of the simple intuitions to remember. And now, so this point, we can write it in a sort of notation. Point, we can write it as P is equal to, in high school notation, you would probably write it as xi plus yj. Isn't it? There's an x component to it and there's a y component to it. So far, so good, right? We could also write it, but in a more sort of a formal notation, we write it as a column vector. People typically write it as xy. There's no difference between these two. They're just different styles of writing the same information. In machine learning community, we tend to write vectors as columns. Column vectors. The first component, the second components, we vertically stack them. Why is this a good idea? See, if you use ijk, right, then what happens after you reach z and you have more features? You run out of indices, isn't it? You have to cook up newer and newer indices. It's just simpler to use a simple notation. Forget about ijk, isn't it? And then if there are too many of them, you can put ... in between. Right. So for example, if it was n dimension where n was 30, you could say x1, x2, and then xn. Right? Assuming there's a column, a stack of all those component numbers. That's why in machine learning, we use this notation. Now look at the gradient. This gradient is defined. Gradient of G is here. is defined by definition is gradient. Are we together? Now, let me use a color for gradient, a different color. I will deliberately use gradient of G. It's a vector. It is this. It is the definition. It is that vector which is made up of the partial derivatives of that, right? So now in this particular example, let us go back and compute our G x y is equal to x square plus y square is equal to some constant square. Gradient of G xy is equal to what? It is equal to 2x. Again, I'll just repeat the whole thing from here. Gradient of G x and gradient of G with respect to y. It is this vector by definition, almost by definition here. And this is equal to what? A 2x, 2y. Now, this is an interesting thing. In this special case, in this case of
It should be y by x, right? Yeah.
y. What do you mean by yx?
Because the gradient is a slope, right? The slope here for the p would be y divided by x, right? The circle that you have.
No. See, this is it. This is the definition of gradient.
Okay.
This is the definition of gradient. Right? So it is this. Are we together, guys? So you agree with this? I have not done anything so far. I have taken the definition and applied it to this particular circle as a constraint surface. And now you notice, now, what is P? P is just xy. It is the point xy, isn't it? So is there a relationship between the gradient and the point? For the circle.
Yes.
Yes, for the circle, gradient G happens to be is equal to 2 times the x vector, the p vector itself. Does this make sense? In this particular case, if you look at the value, and so it is equal to 2 times xy, right? Which is equal to 2 times the p vector. Do you see the connection here, guys? So you say, well, in the case of a circle, there is something interesting. Let me show what it means geometrically. If p vector is this, therefore, what is the vector for G? G is essentially the same vector at twice the length. This is grad G. Would you agree? Isn't it? And that is a crucial insight. What we are saying is, so let me summarize the point. So we find for this special case, I wouldn't use the word special, for this specific case, grad G points in along P, right? So let's not worry about a factor of 2 and so on and so forth. Right? So magnitude we are going to ignore. It points in that direction. But more crucial than that, and is perpendicular to the tangent of the circle at P. Would you agree with this statement? This is a statement that is perpendicular Let's see if this is true. I just made a big statement. I'm saying that this blue line gradient is perpendicular to the circle, perpendicular to the tangent of the circle. What is the tangent?
Line that will go across the P on the circle.
This is the tangent at P. Would you agree?
Yes.
The green line is the tangent. And what is grad G doing? It is perpendicular to the tangent. So far, so good. And this will always be true for any other circle that you draw. If you do another constrained surface, the same reasoning will remain true. Right? So now, without showing this, because it gets into calculus, I'm using this very simple example to make a statement, which I'll make in a moment. Now, notice that first it is perpendicular to the circle. What is the circle? Circle is the contour. Like, it is the point at which r squared, the constant, remains the same, isn't it? So it is perpendicular to that. Now, if I want to go in the direction of maximum increase of value of G, so suppose I take a point, let's take a point, one more color is called for. Let us take a point, this point Q. At Q, if I go in this direction, parallel to this contour surfaces, let me draw one more contour surface here. So if I go along the curve, is G increasing or decreasing?
Unchanged.
Unchanged. It remains the same if you go tangential to the constraint surface. On the other hand, if I want to go in the direction where it increases most, what about going in this direction? Is that the best way that I can do? Go in any arbitrary path, but slightly move outwards, isn't it? You're increasing your G. But what is the way to increase G? So suppose you are allowed to make only 2 steps, right? You said, in all of our stories, there's always, in all mythologies, there's a story that somebody is asked to take only 1 step, and whatever he can cover or she can cover in 1 step belongs to the person, right? So suppose you had to take a 1 such step, and you want to increase your G as much as possible. In which possible direction would you move your G?
Perpendicular to the tangent.
Perpendicular to the tangent, exactly. So you would want to go in the direction, this direction, at Q. Grad G at the point Q, whatever it is, that direction you already realize is perpendicular to the surface. So the path of greatest increase in G, and that is the intuition, the path of, I'll write the point inside. The path of fastest increase of G xy is perpendicular, and we won't use the word perpendicular. The word people often use is normal, because perpendicular is with respect to line. When you go perpendicular to the surface, the wording, it means exactly the same thing, but people use the word normal to the some r square, some constant surface. Here it is a line, it's a curve, but imagine that it's in higher dimension, it would be a sphere, perpendicular to the sphere. Where's my sphere gone? Okay, it's somewhere. Oh, there it is. So imagine it would be the line from the center of the earth penetrating straight up to the sky, isn't it? So this is a very interesting fact. And now I will generalize. I'm going to say that whenever you get any kind of a complicated surface, what is true of a circle or a sphere is true of ellipse and ellipsoids, right? Because locally, an ellipse or an ellipsoid looks like a circle. You wouldn't know whether it's part of a circle or an ellipse, isn't it? So it's true for ellipse, but it is actually, surprisingly, this statement is universally true, right? Grad G will always point orthonormal or like normal to the constrained surface. Are we together? Well, that is very good. And it is also the direction of most increase and represents direction of greatest increase in G. This is our key result that is true. However complicated your surface is, like, it will still be true. At this particular point, right? So if you have a lot of surfaces like this, I don't know, at this point, it will still be the gradient, right? A gradient would be the direction of maximum increase, and it will be perpendicular to the contour surface, constrained surface. Now, with that digression in mind, now comes the key thought. So far, are you folks with me? Right? I hope what I said was simple mathematics, but this mathematics has far-reaching consequence. Now, with this mathematics, come here. Look at the red circle and one of the contour lines, right? The contour line being whichever one it was, that P, the contour line P. So what can you say at the point at which the contour line has some, the yellow lines are error lines, right? Error surfaces, curves of constant error, isn't it? The yellow lines, let us notice this. The yellow lines, well, not lines, yellow curves are error curves, right? Curves, surfaces, more generally. B, red line red curve, red circle is the constrained surface. Right? So G of beta is this, and this yellow one are the error associated with the beta at that particular point, isn't it? The error associated with that. At this particular point, we can tell what the error is because it's a point in the hypothesis space, and we can also compute the value of G. Does that make sense, guys? Right? Now, what do you say? When these two surfaces just tangentially touch each other, think about it. Where is the gradient of, at this point, P, where is the gradient of the red circle pointing? This way. So this is gradient of G, right? And in which direction is the gradient of the error surface pointing? Towards the opposite direction. Let me just mark it as big bold. So would you agree? This is gradient of the error surface. This is the direction. We'll ignore the magnitude. Let's not worry too much about how much big one is compared to the other, right? But the directions are opposite, isn't it? If two vectors have opposite directions, what can you say about them? Would it be fair to say that the gradient of E of the error surface at that point is equal to, up to a proportionality constant, because magnitudes will be whatnot, up to a proportionality constant, the same as gradient of G with a minus sign. Why minus sign? Because if you put a minus sign, then you can be sure that lambda is positive. Right? You can give positive values to lambda. So would you agree that this equation captures our discovery? Because here, when we look at it, this is gradient of G, and this is gradient of E, isn't it? So this equation holds true. Would we say that, guys? Ask me questions, guys. Stop me here, because this is a very, very crucial point. Do we agree?
I have a quick question.
Yes.
So in the inside, you mentioned like path of fastest increase. What exactly does that mean in this context?
In this means, if you have a circle, what is the constraint? It is R, the radius, right? Square of the radius. What is the fastest way to increase this? Go outwards.
Oh, I
Go
see.
radially outwards. That is the path of greatest increase of radius, isn't it? How do you increase the, you are at a point, you want to increase the radius, just go out, isn't it? Radially outwards.
Yeah.
Sonal? What is the point? I mean, why do we have a constraint surface? Okay, just say that we don't want our betas, the parameters, to become big. So we say that we will stay tightly close to small values of beta. So small values of beta, we're saying I have a budget. None of the betas can be more than, let's say, some constant, right? So what happens? It puts you in a circle, isn't it? Because the sum squared values of all the betas must be less than some constant. You're saying within the circle, you're close to the origin, so all the values of betas are small, and that's what we want. We don't want to go out. Always around the origin, because you want to make it small, right? Small means that's all. Yes.
So when you say the constraint, right? Like, but the whole point is to use the gradient descent and reduce the errors. So
No. Gradient descent has already found for you this nice parabola, and it has found this the true optimal beta star, and it has made this nice other equi-error surfaces, A, B, C, D, E, F, G. So your learning is over now.
Oh, okay, so this is after the learning.
After the learning. Yes.
Where is our optimal point where you can say that?
Yes, exactly. So you've already discovered your bowl. You built it. You know where its absolute minima is. Now you're saying, well, you know what? We are not going to go that. We want to be just close to it, not go to that best beta star, because we know that in reality it's not really the best, right? It leads to wild oscillations. It doesn't work for test data. It only works with training data because it has gone and fit to the noise.
So Asif, how do we know that constant? So it's relative, right? So how big?
Yes.
By looking at the residual plot or something like that?
Yeah, we will learn about that. Hold that thought in your mind. I haven't told you how that constant comes about. But at this moment, guys, what I have done is, without this little mathematical digression, has taught you not just this, what is very relevant to regularization, has actually taught you one of the deepest or hardest themes typically people face in college calculus, called constraint optimization. What you have just learned is the calculus of constraint optimization. This lambda in calculus has a name. This is the famous Lagrange, oh my goodness, I will massacre the name. Lagrange, I hope it is Lagrange multiplier. It is the famous Lagrange multiplier. And what this equation says, I will rewrite this equation here. The equation we came up to is that the gradient of some function E is equal to minus, in this particular case, obviously, I made it very real with respect to this, but it is a general truth in mathematics. When you have a constraint and you want to find the minimize E, given this constraint. So in other words, find a point at which E is as small as it can be, but it cannot violate the constraint. You cannot go out of the circle. This equation is called the Lagrange, this is called the Lagrange multiplier.